Hey guys, it's Mr. Vols here. If you are watching this video, that means my wife has had a baby and I'm not here. I'm at the hospital. Um, so here we go. We need to talk about circular motion today. Let's actually go back in the notes that you should have right now. You should have out your circular motion notes, and let's go back and review what we talked about before. We talked about centripetal acceleration and centripetal force. This formula right here is the formula for centripetal acceleration. If you don't have this written down in your notes, you probably should write it right now. Centripetal acceleration, there's your formula. We talked about centripetal force. The formula for that starts with F equals ma. This still applies in circles. Don't forget that that's Newton's second law. The only difference is the sum force in a circle is called the centripetal force. Remember that the centripetal force is the sum of all the forces that are causing an object to stay in a circular path. So instead of the sum force, we're going to use centripetal force. And that centripetal force, remember, is not anything specific. It can be any force. If a ball is twirling on a string, the centripetal force is supplied by the tension in the string, the force of tension in the string. If you have a car going around a turn, the centripetal force that's keeping that car in that circular path is the friction on the wheel. That's what keeps it in the turn. So centripetal force will be the sum of the forces in this case. Mass stays the same, but acceleration in the circle is called centripetal acceleration, or AC. And that's this right here. That's what we just got. So all we're going to do is we're going to start with this equation, substitute FC into here. Substitute this acceleration equation, v squared over r, right into here, and that's what we get. So this here is your acceleration, or your centripetal force equation. So you should write this equation in the box for centripetal force. So this is basically F equals ma, but A for centripetal acceleration is v squared over r, and we just substitute that in for A. Don't forget that radius still has to be in meters, velocities still in meters per second, masses in kilograms, forces in newtons. Okay, centripetal force can be supplied by lots of different things. When you're talking about the Earth, we're in orbit around the sun. Our centripetal force is supplied by the gravitational pull of the sun. That's what keeps us in orbit. We talked about if the sun were to cease to exist, we would fly off in a straight line through space because that force is no longer there. So the sun's gravitational pull is our centripetal force. If you're swirling a ball on a rope, the centripetal force is the tension in the rope or the chain. And this gets a little more complicated when we talk about circles that are vertically spinning as opposed to horizontally spinning, but we'll get to that in a second. On turning wheels, if you're turning a corner in your car, the force of friction on tires is the centripetal force in that case. So again, centripetal force is just any force that keeps an object moving in a circular path, and there's any number of forces that can supply the centripetal force. Note that once that force is gone, Newton's first law says the object is going to fly off in a straight line in the direction of its velocity. So I'll ask you a question. What happens if you're turning a curve and you hit a patch of ice? Of course, you know the answer is that you're going to fly off the curve in a straight line in whatever direction you were going, because the force of friction was the centripetal force keeping you in the curve, and all of a sudden now it is gone. You lose the force. That's the force that was keeping you in a circle, so you no longer are moving in a circular path. You're obeying Newton's first law, and you're moving in a straight line. You may not know this, but that's what happens when you throw a baseball. You're moving that ball in a circular arc until at some point you let the ball go. And at that point, the ball ceases to move in a circle, and it moves in a straight line, whatever direction it was going when you released it. So pitchers in baseball have to be so good at knowing when exactly to release a ball so that it will go in a straight line towards its destination. Of course, you and I know it doesn't actually go in a straight line because of the force of gravity. It will end up dropping just a little bit. All right, let's move on. We need to talk about the speed of circular motion, the speed. The circular motion that we're going to be talking about is uniform circular motion, which means that speed is constant. Speed is constant. It's not going to be changing. And you know from before, from way back at the beginning of the semester, we talked about speed, and we can easily calculate speed if we know the distance that we traveled and we divide it by the time it took us to travel that distance. So if you move 10 meters in 5 seconds, 10 divided by 5 is 2, and your speed is 2 meters per second. All right? It's the same thing in a circle, except that in a circle, the distance you travel is the circumference of a circle. And if you remember from your geometry class, the circumference of a circle is given by this equation, 2 pi r. So all we're going to do is simply substitute 2 pi r in here for distance. And our speed equation ends up being this. V, or speed, equals 2 pi r over t. Now, make sure that when you write this in your notes, this goes in the next box in your notes. This t is very important. Make sure that it is capitalized, not lowercase. Capital T is a very important kind of t. It's still time, and it's still given in seconds, but this capital T is a very special time. It's called the period. And the period is the amount of time, or the seconds, that it takes to complete one revolution. In other words, one trip around the circle. However long, however many seconds it takes to make one trip around the circle, that is the period. That's why it's given down here in seconds per revolution. T is the amount of seconds per one revolution. Velocity, still meters per second. R is the radius of the circle. So velocity is given, circular velocity is given by 2 pi r divided by the period. Sometimes we'll be given information in RPMs. You have a reading on your dashboard that's in RPMs. You may not have known this, but that stands for revolutions per minute. And we can't use this. We have to convert this. We have to convert RPMs to period before we can do anything with it. In order to do that, it just takes 2 steps. We simply convert the time component of that to seconds instead of minutes. And then all we have to do is flip it. So here's an example problem that we're going to talk about. Let's talk about the tachometer in your car. That's what reads the RPM. It reads 5,000 RPMs, which, by the way, if you know anything about RPMs, that's a very high RPM value. You're probably revving your engine at this point, maybe trying to pass someone in the fast lane, which I know none of you do because you're all good drivers. 5,000 RPMs. Question is, what is the period? The RPM is the revolutions of your engine. I should have said that already. It's the speed that your engine makes when it's going around. That's how many times it goes around per minute. And we want to know the period. In other words, we want to know the amount of time that it takes for one revolution. This is the number of revolutions your engine makes in 1 minute. So we need to convert that. So here's the first thing we do. We first converted this time component into seconds. We can't use minutes. We always use seconds. 1 minute is 60 seconds. This was, remember, this RPMs, revolutions per minute. This was 5,000 revolutions per minute. So that's the same thing as 5,000 over 1 minute. 1 minute. Let's see if I can write this here. Terrible. 5,000 RPMs, 5,000 revolutions per 1 minute. All we did is flip that. We put 1 minute on the top, 5,000 revolutions on the bottom, change the minutes to seconds, and divide 60 by 5,000. That gives you the amount of time in seconds per one revolution, which is 0.012 seconds per revolution. So the period for this engine running at 5,000 RPMs is 0.012 seconds. It takes 0.012 seconds for this engine to make one circle, to make one trip around the circle. So this should go in the space underneath this problem here, not in the box underneath it. We'll put something else in that box. Alright, this is the first box. You can write this down if you want, but you don't have to because it's the same formula we just dealt with. 2 pi r over capital T, the period. That's what you use if you have the time it takes to complete one revolution. That's the period. If you have the period, you use the formula with the period. Very simple. Or you can use this one if you're given different information. If you're given the amount of time it takes to complete more than one revolution. So sometimes the problem will say something like, a ball is whirling in a circular path and it completes 10 circles in 10 seconds or something like that. That's more than one revolution. It doesn't give us the period. So in order to calculate the speed from that, we would use this formula where x is the number of revolutions that we're talking about. And t, notice this is lowercase t now, not uppercase. T would be the amount of time that we're dealing with. So 2 pi r times x divided by the amount of time it takes. This formula is not in your equation chart, and I'll tell you why. It's because it's kind of intuitive. I will make it available to you, but in effect, what you're doing by dividing the number of revolutions by the time it takes is you're calculating the period. So this formula is really the same as this formula, and you can always use this one if you want. It's just that if you have this information, the first thing you need to do is calculate the period and plug that period into here. In effect, that is what you're doing with this equation all in one step. I hope that makes sense. 2 pi r x divided by t, lowercase t. So let's look at this sample problem. You have a rubber stopper on the end of a 0.5 meter long string, that completes 10 circles in 5 seconds. Okay, so once again, we have 10 circles, not one circle. So we're not going to use the formula with period in it. We're going to use this one, the second formula we got. 10 circles in 5 seconds. What's the velocity of the stopper? It gives us the radius. That's the length of the string. So we've got this string here, and it's got a ball on the end, and the ball is turning in this circle. Actually, the circle should be more like this. It's going like that. The length of the string is the radius of the circle, r. So we simply plug everything in. 2 pi times the radius, which is 0.5 meters, times x, which is the number of revolutions, 10 circles, divided by the time. Total time is 5 seconds. And if you do that, you should come out with 6.28 meters per second. I want you to look at these two wheels in your notes. What it says is when a circular object rotates, it takes the same amount of time for the center of the circle to complete one revolution as it does for the outside of the circle to complete one revolution. The reason is because it's on the same object. They have to be moving at the same speed because they're on the same object. It takes the same amount of time. But the question is, which part of the wheel, the center or the outside, has the greatest speed? So you can pick a point on the outside and you can pick a point toward the center. And as they move, which one is going to have the greatest speed? I'll give you a minute to think about that. Okay, I hope you chose the point on the outside has the greatest speed, because even though they're going around the circle in the same amount of time, this point on the outside is going a farther distance than the point on the inside. The outside circle has a larger radius, larger distance in the same amount of time, so it must move at a greater speed than the inner part of the circle. Alright, let's move on. Centripetal versus centrifugal force. We did this little demonstration the other day. I spun a bucket of water over my head. Why doesn't gravity pull the water out is the question. Give you a minute to ponder that. Well, the real answer here is inertia. Remember, Newton's first law says that an object in motion wants to remain in motion. And I'll ask you this question. What is the motion of the object, the water in this bucket, as it nears the top of the circle? Well, the water in the bucket is moving in this direction. And Newton's first law says when you are in motion, you want to remain in motion in the same direction you're moving. So this water actually has no reason to fall down because it's going to obey Newton's first law. It's going to keep moving along this path. The only reason it changes directions is because of the